All righty. Okay. Welcome to our session today. I'm going to go ahead and get started right away. You should have a copy of your equation quiz handy. If you don't have that handy, go and grab your equation quiz. Go and grab your calculator. We're going to do some problems in class today. So if you don't have those items, I'll give you 2 or 3 minutes to get that. Okay, if you have your calculators and your pencils and your paper, we're going to get started with some problem solving today. Today, I want to just walk through some problems with you before I conclude this chapter. I'm going to share my screen. Let me see what this is. Okay, I just sent this to you, so you may not know that you have it. I just tried to get it to you before class started. So what we're going to do now is work out a few problems together. I want to do these very, very slowly so that you can sort of grasp what is being asked in the question, so that on our next exam, which will be chapters 5 and 6, you will do well. So you see problem number 1. Let me go and see if you all are putting your names in, see who's in class. Okay, so I want to say welcome to Kaylin, Kendra, Keston, Monier, Nigel, and Lanisha. Okay, we're missing Morgan, we're missing Lex, and let's see. And I don't know what happened to Yasmin. He hasn't been in class in a while. I need to check on her again. Okay, so here we have a problem. So let's see how we're going to attack this problem. The mass and radius of the moon. So now we're given some information. So this is what I want you to do. When you first see some numbers in a problem, you're going to write those numbers down. So it says the mass and radius. So the mass is given. Okay, and you can notice right away that this number is 10 to the 22nd. Remember, the Earth had the exponent 10 to 24th. So of course, the Earth is more massive than the moon. We know that already. And also we see that the radius here is smaller than the Earth. So the radius is only 1.7 times 10 to the 6 meters. So even though we know that they are smaller, look at this. This radius is 10 to the 6th. For the Earth, the value, the exponent is also 10 to the 6th. So keep in mind then that the moon, although it's so far away, the radius here is comparable to that of the Earth. Okay, the question is, what is the weight of a 1 kilogram object? So what is the weight? We're looking for the weight of a 1 kilogram object on the surface of the moon. So that means that this is the mass of the moon, and this is the mass of my object. So I want to distinguish between these two. And this is only 1 kilogram. So that makes the problem easy for us to solve. So what are we going to do? Who can tell me? Now, let me go back now to, let me share something else very quickly with you. Let me share. Let me share here, okay, on this page. So here we have the numbers. So who can tell me the equation that I'm going to use to solve this problem? Just give me a number. Go into the chat and tell me which of these equations am I going to use to solve this problem. Am I sharing the equation quiz?
Yes.
Okay, great. Okay. So which of these equations, I know what's given, so my next step is to decide how am I going to tackle this problem. So let me see what someone is saying. Okay, someone said 29. Okay, I'm not thinking that. Now, okay, let's just see what 29 says. 29 says the centripetal force. So what does that tell us? The centripetal force class is on your paper, you should have F sub C, which is M A sub C. A sub C stands for the centripetal acceleration, and which we have defined that to be velocity squared over R. So even if you started with that, which is an okay place to start, even if you start with that, from what we have given in our problem, the mass of the moon, the mass of the object, the radius of the moon, that would not be where any of our values would fit. So that's one person's question. One person's answer. I want to explain that. Anyone else? What equation would we use to solve the problem? Now let's go back to what they're asking for in this problem. Oh no, it went away. Wow. Let me put this on my whiteboard, and that way it won't go away. Give me just 1 minute to get my other sheet of paper. Okay. Wish I could copy and paste this to my picture, but I don't think I can. Okay, so I'm going to go to the whiteboard so that it won't go away when I go back and forth. Okay, so in that problem, we were given the mass of the moon. We were given the radius of the moon. We were asked to find the weight of an object, and we were given the mass of that object. So we're gonna let lowercase m with no subscript. We'll just say mass of the object, just to be clear. Okay, so the mass of the moon was 7.4 4 times 10 to the 22nd kilograms. The radius was 1.7 times 10 to the 6 meters. We're looking for the weight of an object whose mass is just 1 kilogram. Okay, now look carefully what we have given. And let's go back now to our equation sheet. I want you to be able to tell me how would I start solving this problem? In other words, on this sheet, there's an equation that says the very thing we're looking for. So who can tell me what that equation is? Okay, I'm waiting to see who can tell me which equation I'm going to use. I'm looking for weight. I got Lanisha, Nigel, Monye, Keston, Kendra, and Kaylin. Someone should be able to, even if you're incorrect, that's okay. That'll give me a chance to say something in response, but you have to give me some answer.
The equation quiz don't have the equations on there.
Well, that was okay. Thank you for saying that. So that's what you are supposed to do. You are supposed to have your own copy. I sent this to you and I said that you are to complete the equation quiz. All the equations that I've given you before are the ones that I did not highlight. And then the ones that are highlighted are the ones that you are to use to complete in this chapter 5. So who knows the equation for Newton's second law? Type it in if you know that equation, Newton's second law. Okay, Lanisha, that's a good start. Okay, looking for weight, that's a good start. Okay, Lanisha gave me a good answer. Okay, Kaylin, thank you very much. So now, Keston, thank you very much. So we have an equation, Newton's second law. I keep making my F's. Let me make that a little bit better. Okay, and that's Newton's. Okay, who can give me the equation for weight? What's the equation for weight? Okay, very good. We use lowercase w. Weight is mg. Very good. Thank you, Keston and Lanisha and Kaylin and Nigel. Okay, very good. This is measured in newtons or can be in pounds. Now, we said that the weight of an object is the gravitational force between that object and the surface that we're weighing it with respect to. So for example, we said that on the Earth, this is the Earth now, and this represents the radius of the Earth. Listen very carefully. This object right here has a weight. Now, if we know the value of G, we just say weight equals mg. But in this problem that we're going to solve, we don't know the value of G on the surface of the moon. So therefore, we cannot solve it so simply. But we can solve it based on what we were given, because we also know, as I just said, that the weight is the gravitational force between that object and between the two objects. So now what the author is saying is that to find the weight on the moon, we must find the gravitational force between that object and the moon. So now the object is sitting on the surface of the moon. So this is the radius of the moon, and the object is sitting here, 1 kilogram object on the moon. That's a poor circle, I know. So then what do we say up here? What was my equation? My equation said that the weight is equal to the gravitational force between the object and the earth. And we're measuring that to the center of the earth. So even though it looks this way, we think of it this way. We think of it, here's the object, the radius of the earth, and then we go to the center of the other object, which happens to be the earth. And so F sub G, what does F sub G say? F sub G, which is the gravitational force, is big G mass of the what? Earth. If it's on Earth, we just call it mass 1. Mass of the object, this case a person, divided by the radius between them squared. If it's the Earth, it's the radius of the Earth. If it's the moon, it would be the radius of the moon. So that's what this question is asking you to do. It's asking you to solve this equation because it gave you the mass of the moon, that's object 1, the mass of the person, that's object 2, and it gave you the radius between the moon, center of the moon, and the object. So this is the equation that we're going to solve. So now, I need for you to go and solve that equation. Okay. So please go to your paper and solve that equation, and let's see who gets the correct answer. When you get the correct answer, put it in chat. So I need for you to work this problem out very, very quickly with your calculator and your white paper and your paper. Okay, I'm waiting for you all to solve the problem. If you're having problems looking at the value of G, so the equation you're solving is F sub G, which is the weight, which is big G, okay? Big G times the mass of the moon, the mass of the object, divided by the radius of the moon, and that has to be squared. So if you're having problems finding the value of G is 6.67 times 10 to the minus 11 Newton meter square over kilogram square. Now, I'm doing this exercise for several reasons. One reason I'm doing this exercise is because I want to see what you are doing and what you are learning. And as I stressed initially, and that's why I went through the trouble of preparing you the equation quizzes. If you don't know your equations, I don't have some idea of where to start, which is with an equation, you won't be able to solve the problem. So the problem I'm seeing now is that when I ask you for the equation for force, for Newton's second law, that was slow in coming. The equation for weight wasn't so slow in coming. But also, it's like you all are not internalizing the concepts. So the concept here, as I just went over, is that weight is the attractive force between the objects. In this case, the object and the moon. But you have to know that to know where to start. Now, I'm not getting any answers that are correct. So let me see what the problem is. Maybe I did mine incorrectly. Let me just go again and let's see if I can't solve this problem with you, okay? So I substitute in the value of G. Now the mass of the moon. So the mass of the moon is 7.4 times 10 to the 22nd kilograms, okay? The mass of the object is 1 kilogram. And I'm going to divide that by the radius of the moon squared, which means I'm going to square 1.7 meters, that's to be squared, and I'm going to square 10 to the 6th. And of course, 10 to the 6th squared is 10 to the 12th. Okay, make sure you understand what I did there. So now I need to just put the numbers in my calculator, because you see, I can already see that I'm going to have minus 11 and positive 22. It's going to give me positive 11. So I have 10 to the 11th in the numerator. I'm going to bring this one up, and it's going to be negative. So I'm going to have 12. So after I go through all these numbers, I'm going to have 10 to the minus 1. Take care of that first. Then I have meter squared. That's going to cancel that out, okay? 17 steps to be squared. Kilogram, that's going to be canceling out. So I know my answer is going to be in Newton. So now I've taken care of everything but the numbers. So now it should be very easy in my calculator to take 6.67 multiplied by 7.4 and divided by 1.7 twice. You should not have difficulty doing that. So please see where you're making an error if you're not getting the answer that we should be getting. So I'm liking the answer that I'm getting from Lanisha. I still have okay, Monier, you're still a little off, but you're getting close. Okay, so when you multiply 6.67 times 7.4 and divide by 1.7 twice, what do you get? Do you get 17.07? Okay. Now, what does this 10 to the minus 1 mean? That means that I am to find my decimal and move it to the left one place. That's what it means. So when I do that, then I get 1.7 newtons. That's what I should get for my answer. Now, if you're not getting that answer, please keep working until you get that answer, because there's no reason why, after I put the numbers here and you have your calculator, that you aren't getting this answer. So please check and see why you're not getting this answer. And then I want to move on. But I want to make sure that you get that answer, because this is one of the simple problems that we're going to have on the exam. I want to know what is the difficulty. So I will accept the answer from Lanisha. Let me see who else. Lanisha, you're good. Keston still needs to do his again. Nigel to do his again. I think only Lanisha has the right answer so far. Okay. Okay, so Kaylin, did you get that answer by solving for it? Is that what you got when you solved for it? I know you can copy it now from the whiteboard. I want to make sure you understand it. So if you understand it, then you can put in the answer. If you still get something different, then you're not ready to put your answer in. So it doesn't help you to put the answer down if you're not getting that answer. Okay, okay, very good. All right, so let me see. I'm trying to see what Nigel's final answer is from his calculator. Okay, do this for me.
It was 17 when I.
Okay, go ahead, Nigel.
Can you hear me?
Yes, I can.
It was actually 17, but when I moved it over, I didn't take off the 10 to the -1.
Okay.
And that's why it was like that. But I got the same answer.
Okay, great. All right. Okay, Keston, your answer looks good. All right, very good. Okay, so maybe by doing this, we can see what are some of the common errors that we're making, like not moving the decimal place over again, or not squaring. In this case, we see R has to be squared. You don't do that, you won't get the right answer. So let's just see what some of the common errors we're making as we go through this assignment. Okay, so our next problem says, an object weighs 10 newtons on the Earth's surface. What is the weight of the object on a planet that has 1/10 the Earth's mass and 1/2 the Earth's radius? Okay, let's go to our whiteboard and let's share this problem. Okay. Now, before I take this away, please pay close attention to this equation. You notice here that in order to find the weight, we have to know the value of G, that's a constant, the mass of the object, the massive object, the mass of the object, that's in this case the Earth and the planet and the object, and the radius. So we're going to be using this equation with our new information. So let me show you what I'm going to do. And I'm going to clear everything. I'm only going to clear some things. I'm going to clear that too. Now, this is what I mean when I say that I want you all to be able to solve these problems quickly, as opposed to having to go through the long method. And I'm going to show you what I mean right here in this problem. That's why I wanted to use this problem. Okay. So it says, an object weighs 10 newtons on the Earth's surface. So we know the weight on the Earth is 10 newtons. Okay, give me 1 second. I got someone at the door. Give me 1 second. Okay, I'm back. Okay. The the weight on the Earth is 10 newtons. What is the weight of the object on a planet? So I'm looking for the weight on some planet that has 1/10 the Earth's mass. So that means that here, we're going to say Earth now. So we're going to take this. Right here, we're going to say that this is 0.1 of the mass of the Earth. Okay, that's the mass of this planet. Let me see, someone has a question. Hold on. Okay, class. And then it says, so it says that has 1/10 the Earth's mass. So 1/10 means 0.1 the mass of the Earth. It also has 1/2 the Earth's radius. That means I have 0.5 of the radius of the Earth. Now, if you're thinking that I need to come here and put the mass of the Earth, okay, so I want the weight on this planet. I want the mass here of the planet, the mass of the object, and this is the planet. Now, what I want you to do and watch very, very carefully is notice that when we define the weight, we said on the Earth now, this is on the Earth, we said that that was big G, mass of the Earth, mass of the object, divided by the radius of the Earth squared. And that gave us the 10 newtons in this case. So now, what you want to do is say, okay, then the weight of the planet, the object on the planet, is big G. Now, rather than having the mass of the Earth, I have 0.1 mass of the Earth. Okay, mass of the object divided by not the radius of the Earth, but the radius of the planet, which happens to be 0.5 times the radius of the Earth. Now, do I need to put in the radius of the Earth and the mass of the Earth and all of that? No, because remember, we said that when we did it before, we found out again, we define weight as mg, and we define weight as mg on the planet. So what is different in this equation? I'll call this equation 1, and this equation 2. What is different? What is different, class, in this? Okay, this is the object. If you notice, then the only thing that's different is here. What is different is I have 0.1 here. Here I have 0.5 to be squared. And the rest of it, the rest of this equation is the exact same thing. Notice, the rest of this equation is big G mass of Earth, mass of the object, divided by the radius of the Earth squared. Now look, all of this, look carefully, all of this is this. You see that? This is the exact same thing. So the only difference is, for my new value, the weight on the planet will be whatever this number is. So I'm going to take this number, whatever it is, and multiply it by 10 newtons, because that's the only difference in these two numbers. So now I can find the weight of the object on the planet. So let's see if you can give me that answer. What is that answer? I'll see who can get that answer first. Have your calculators out? Work on that answer, please.
All right, Mama, I'll put you.
You get something, your mail?
Yes, dab me up.
Hold on.
Why is Keston doing it?
Get them to learn something.
Keston, you know how to program a computer? You ever know how to do program?
Okay, very good, Nigel. Nigel has the answer. Anyone else? It can't just be Nigel who's Monnier. Okay, now Monnier, very good, almost. Look carefully at what you have done. I need you to complete that. I'll give you a clue, Monnier. You need to complete what you have done. Look carefully at what we have here. Okay, Monnier, I'm waiting for you to give me a better answer, but you're almost there. So I'm pleased with the work that's being done by Nigel and Monnier. I need to hear from Lanisha and Keston. Need to hear from Kaylin. Lanisha, we're on question number 2 from the from the in-class assignment. Question number 2. Okay, Keston, 4 newtons, that's good. Okay, so I haven't heard from, I know some of you are going in and out, you have poor connection, I understand that, but I need to move on. So what we're going to do then is we're going to take 0.1 and divide it by 0.5 squared. And when we do that, we get 0.4. 0.4. Now, 0.4 times what? 0.4 times all of this. But we're not going to solve all of this because all of this we said is equal to that, and that's just 10 newtons. So multiply that by 10 newtons, and of course we get 4 newtons. But what I want to point out to you in this problem and in similar problems that we're going to be doing is that you understand how to simplify the problem. Simplify the problem. Now, I've given this problem before, and this is why I wanted to go over it, because what some students have done in the past, and this is very laborious, what they have done is, okay, they know that the mass is the same on the earth and on the moon. So they find the mass. In other words, they say, okay, I know that weight equals mg. So I'm going to find the mass of the object. And they go through that, all of that. That's the mass of the object. Then they put in the mass of the earth, the value of big G, the radius of the earth. I'm sorry, over here. This number, they put in this number, and then this number, and then this big G, and the mass of the object that they got from right here, which is the same. And they solve all this big laborious problem. So I'm trying to tell you that one of the tools that you are supposed to get from this class is called critical thinking. In other words, you have to relate what you have learned to every new situation so that you don't spend time going through a laborious problem like this, which is very, very time consuming. Because once you see this and you recognize the pattern, this is how you will solve it every time. Okay? So if the mass of the planet is half that of the earth, you're going to just say 0.5 mass of the earth. If it's 7 times radius, you're going to say 7 times radius of the earth. You're not going to go through a long problem the way we did in the previous problem. In the previous problem, we had to do it that way because that's all we were given. And this next problem, that's why I wanted this problem to follow that problem. Now we see what is meant by all of this. And remember, do not forget that we've already solved for the value of G using the same equation. Look in your notes, it is there. Okay, any questions before I move on? Okay. Let's go to this problem. So this problem says a 2,400 kilogram satellite is in a circular orbit around a planet. The satellite travels with a constant speed, 6,670 meters per second. The radius of the circular orbit is this. The question says, at the instant shown in the figure, which arrow indicates the direction of the net force on the satellite? Okay, at the instant that is shown right here. The question is, what is the direction of the force? Okay, so in chat, just choose a letter. Okay, A, B, C, D, or E. A, B, C, D, or E. Which of those give me the direction of the force as the satellite is circling this planet? Okay, give me your answer. Okay, I'm looking at several answers. Okay. Now, let me see. Well, let me just go ahead and explain what the answer is and why. So one of the things that we learn is that for the centripetal force, you see, when anything is moving in a circle, the force on it is the center-seeking force, and we call that force centripetal. So we have the equation F sub C. Centripetal is center-seeking, which simply means the force is always directed toward the center. So that means that if it's right here, it's directed toward the center of this circle. That's what it means. Now, previously, when we were discussing forces, we said that the force was in the same direction as the acceleration, but we're talking now about a center-seeking force. So it's always directed toward the center, okay? Now, the equation for that is mass times the acceleration, centripetal, and we define that as V squared over R. So now let's use that in the second part of this problem. Okay, so the problem here is, clear. What is the acceleration of the satellite? So let's go to our whiteboard and solve this problem. Okay, so based on what they asked me, I don't need this equation anymore. Okay, but let's first of all, let's write down again what's given in the problem. A 24 kilogram satellite. So this is the mass of the satellite. And it is 2,400 kilograms. Is in a circular orbit around a planet. The satellite travels with a constant speed. So my speed of my satellite is 6,670 meters per second. The radius of my satellite is 8.92 times 10 to the 6 meters. And the question is, what is the acceleration? Okay, so first we know, based on the picture that we saw, the satellite is in a circle around this planet. So therefore, its acceleration is the centripetal acceleration. So we know that the centripetal acceleration, A sub C, is defined as V squared over R. Okay, V squared over R. So now let us find our value. Now let me show you something that I want to show you again, and this is why math skills are so important. Let's write this number here as 6.67. You see, 6.67. Oh, I'm sorry, I'm looking at the wrong number. Yes, I am. 6.67, okay, times 10 to the what? Third meters per second. Okay. If we write it that way, then when we go over here to square it, it's easy to square it, because what I'm going to do is I'm going to square 6.67. I'm going to square that. I'm going to square 10 to the third. I'm going to square meter square second square. In other words, I'm simplifying the problem even before I put it in my calculator. Then I'm going to divide it by the radius, which is 8.92 times 10 to the 6 meters. So the first thing I see, class, is that this to the 10 to the third squared is 10 to the 6th. I saw that immediately. That's why I wanted to write it that way. So that way I can cancel out this part of the problem. And then when I cancel out meter with one of these, then I have meter per second square, which is the right unit. And therefore, when I solve my problem on my calculator, what do I get? Okay, very good, Nigel. Okay, very good, Kaylin. All right. Okay, those two, that's a simple problem to solve. You put in 6.67 and square it and divide it by 8.92. It can't get any simpler than that. Okay, so if you get 4.99, and then we'll go to our choices and see what our answer is. Okay, so let's go back to our okay. So what is the acceleration of the satellite? Then we have what? D. Okay. Okay, we're going to get 4.99, and that's going to be D. Okay. All right. Let's go to number 5. Can you see number 5? Okay, so it says determine the magnitude of the gravitational force exerted on the satellite by the planet. Okay, so let me move up a little bit. Okay, we're on number 5 now. So number 5 says determine the magnitude of the gravitational force exerted on the satellite by the planet. Okay, what we're going to do there? Anybody have how to start the problem? Okay. Does anyone know how to start the problem? We just did a problem where we said gravitational force. No takers? Please look at the question. Determine the magnitude of the gravitational force exerted on the satellite by the planet. What do you think we should do first? No takers? Okay, Someone said, find the gravitational force first. Okay, so now let's just see what would happen if we do that. Remember that the gravitational force, hold on. Gravitational force F sub G, okay, is big G. That's universal gravitational constant. We know what that is. Then we have to have the mass of the planet and then the mass of the satellite divided by the radius of the satellite, or the distance squared. So, do we know the mass of the planet? That's the first question. Were we given the mass of the planet in that problem? Yes or no? Okay, let me go back up to the problem and show you what it said. Okay. We were given the radius of the orbit. We don't even know the radius of the planet. We know the mass of the satellite. We know the speed of the satellite. So this question then should remind us of something else we learned in this chapter. And what we learned in this chapter was that for an object in a circular orbit, the gravitational force is equal to the centripetal force. So these are the things that we have to learn. The gravitational force is equal to the centripetal force. Remember when we talked about an object that's in an orbit around the Earth, the reason why that object remains in its, this is the Earth, this is the object in orbit around the Earth, and the reason why it remains that way is we solved the problem to show that the centripetal force is equal to the gravitational force between the object and the Earth. So if I want to find the gravitational force on the satellite, I can simply find the centripetal force. If I know the mass of the satellite, the velocity of the what? Satellite squared divided by the radius, how far it is out. So now I can determine the magnitude of the gravitational force. So that's what we need to solve in this problem. So remember, we were given the mass of the satellite, the speed of the satellite, and we know R. So someone please solve, you all please solve that problem. Okay, Nigel, very good. Okay, Nigel, very good. MV squared over R. That's what we're going to solve. So put that into your calculator. Okay, if you don't see I'm going to go back up and show you the value for those numbers in case you don't have them. Okay, so here are the numbers. The mass of the satellite, the speed of the satellite, and the radius of the circular orbit. So those are the numbers we're going to put into our equation. And let's see what you get. Look at, okay, look at your numbers carefully now. Make sure you put the numbers in carefully. Remember, we had said we know a trick now when it comes to using these large numbers in order to make them smaller. Remember what our trick was? Our trick was, okay, we're saying that F sub C is mass. So mass we're going to say is 2.4 times 10 to the third kilograms. We're going to say that V, the speed, is 6.67. Okay, we got to say V squared. So we're going to square that. We're going to say 10 to the third. We're going to square that. And we're going to have meter square second square. And then all of that, mv squared, this is mv squared over r, and r is 8.92 times 10 to the 6 meters. So right away, all of this is gone. And then also this meter cancels one of those meters. And we know that a kilogram meter per second square, that's going to give us so many newtons. So now in my calculator, I simply need to take 6.67 and square it, multiply it by 2.4, divide it by 8.92, and take it out 3 places. In this case, I think we have a number there. Okay, so try it again and see what you get this time. Let me see what someone else is saying. Okay. I'm looking at your exponents, Kaylin. Oh, let me see what's going on with the exponents there. Let me see what we're going to get. Let me put in my calculator and see what I get first. So I'm going to start with 6.67 since that's being squared. 6.67 squared. Do that first. And then times 2.4. Get that. And then divide that by 8.92. Okay. So when I do all that, I get 11.97 times 10. Remember, this is the third right here. So that's the third. That's what I get. And of course, my units are newtons. So this is what I get when I solve the problem. Now I've got to decide how to write this. I've got to write this in scientific notation with 2 significant digits, because my smallest number here has 2. So my answer has 2 significant digits. So it's like 12 times 10 to the third, which is going to be 1.2 times 10 to the 4 newtons. Okay? 2 sig figs would be 12. In scientific notation, my answer has to be 1 or greater, but less than 10. Okay? So that's why I have to do 1.2. So this is the answer that we're looking for. Okay, hope you can see where your error is, Kaylin. Hope you can see where you have an error. Okay, Kaylin was the only one that gave me an answer. So that tells me that not only are we having difficulty setting the problem up, I'm wondering if we're having difficulty putting the numbers in the calculator to get the answer. So you want to make sure that you are able to put your numbers in the calculator correctly. And as, let's see, Nigel gave me an answer. Okay, Nigel, I see it now. Very good. I just want you to give me, once you work that out, that's okay. But if you were giving me an answer and I'm looking for you to give me the answer, I would want it to be written like this. But of course, in this case, you would be looking for the closest answer that's in the multiple choice. So of course that would be answer A. Okay. All right. Very good. let's see, we have time for one more. Let's try one more together. Now this one, I'm not going to say too much at all. I'm going to see if after doing these problems that we have done, can we work something out? Okay, so let's just go here. Okay, so the question is, what is the acceleration due to gravity at an altitude of 1 times 10 to the 6 meters above the Earth's surface? Okay, what would be the acceleration due to gravity at an altitude of 1 times 10 to the 6 meters above the Earth's surface? How will we find that number? So do you know where to start? Anybody know where to start? Okay. Okay. All right. Let's go now and see where to start. Okay. So again, the thing about physics that I'm thinking that we are not getting is the cumulative content of the lectures. And I'm telling you that if you want to earn an A in the class, you've got to go back now and commit to your memory or your understanding what we are learning, especially the ones that I take extra time to go over with you. I take the extra time to go over it because that is something that is important, that's going to help you throughout the course, throughout the entire course, not just in each chapter, but throughout the course. So in this question, it asks you, it says, what is the acceleration due to gravity? So we know that on the Earth's surface, first of all, we know on the Earth's surface that this value we have learned is 9.8 meters per second squared. Now, what is that value, they say, if you are 1 million meters above the Earth's surface? So that means then that you have to think critically about where this value of G came from. And we said that the weight is equal to mg, which is equal to big G, mass of the Earth, mass of the object, divided by the radius of the Earth squared, mass of the object right here. This is the weight of my object. And what we did, class, was we canceled all this out. And we put in all these numbers for G. And when we did all these numbers for G, if you look in your notes, we got 9.77 meters per second squared. And we rounded that up to 9.8 meters per second squared. So look in your notes. We did that for a reason. And that's because I knew that in the next chapter, you would need to understand where this value of G came from. So therefore, in this problem that we're doing now, well, the first thing you have to notice is that we're out. So here is the earth. This is the radius of the earth. Okay? And if I was on the object, that would be the weight using this G. Okay? But now I'm at some distance here, which is 1 times 10 to the 6 meters. And the question is, what is my weight out here? Well, the first thing we know is that it has to be less than it would be on the earth. Okay? Because we say that the further you get from the earth's surface, the object has to have less weight, same mass, less weight. But how's it go? But okay, so now G is the acceleration due to gravity. G gets smaller, therefore the weight gets smaller. But what's the value of G? Well, the only thing that's changing in this problem here is the radius. Where is the object? The object is no longer here, where R is the radius of the earth. The object is here. So now my big G is going to be big G, mass of the earth, that's the same, divided by the radius of the earth squared. So now this value now is going to be what? And it told us to use for the radius of the earth, it said use 6.38. So we have 6.38 plus 1. So we have 7.38. Okay, times 10 to the 6. And then this number has to be squared. Okay, radius of the earth squared. So if I was on the earth, it would be 6.38. But I'm above the earth by 1 more million, so I have 7.38. So now I can find the value here. So let's see what you get. Okay, let's see what you get. What is G? 1 meter above the earth's surface. Okay. Now in that problem, you may not have your notes in front of you, but the mass of Earth is going to be 5.98 times 10 to 24th kilograms. And I've already given you 6.38 and add that 1 to it. And now we have the value of G, which is a constant. So you know that value. So go ahead and try to work that out. Okay, let's see if anybody's giving me the answer. No one's giving me the answer to this problem? Let's try it again. Okay, let's try it together. Oh, well, our time is over. Okay, so let me just show you, class, that all you're going to do is put in the value of big G. You know what that is. The mass of the Earth, you know what that is. And the value that we have here for the radius. And now you know what that is. So hopefully when you plug all that in, you will get the answer. Let me go ahead and assign the rest of these for your homework. Tomorrow we'll start a new chapter. I want to review some of the highlights. I have one problem to do. No, I have about three. About 3 problems to solve from chapter 5. We'll do that first, and then we're going to introduce chapter 6. Okay, Kaylin says 9:44. I haven't really worked it out yet, but I don't see that's one of the choices, so I'm not sure if that's correct. But keep working on it, and we'll see. What I'm saying, Kaylin, is oh, that's the other assignment. Hold on, not that assignment. The other one. Okay, so what I'm saying here is that these are our choices. So, and also remember, it has to be a value less than 9.8. Well, all these are less than, so we know that's the case. So we got to work it out a little bit better. And then we're going to do the rest of these as your assignment. So I've sent you, so all you have to do 1, 2, 3, 4 more, because we've done most of these. Okay, so go ahead, and if you don't have any questions, you can sign out, and I will see you tomorrow. I will send you chapter 6 notes in your email. Okay, if you don't have any questions, you can sign out, and I can see if you have questions that I'll answer your questions.
You said that homework's due tonight?
No, I haven't. This homework that I'm giving you is just for you to understand this chapter. And because I don't have time to grade a lot of homework, but you're responsible for all the problems I'm giving you as homework, and I will give you the answers. And once I give you the answers on tomorrow, you can let me know which ones you don't understand. And then I will take the test questions from that. You understand?
Yes, ma'am.
Now, what is due tomorrow, like at noon, is your midterm exam. That's what's due. So do you have that?
Yes, ma'am, I have that. I was just making sure.
Okay, yes. So the homework, I understand about wanting to turn it in, and I will give you a chance to get more homework grades. But remember, the homework grade itself only counts 5% toward your final grade. So tomorrow, I'll probably give a little quiz. I want to give more quizzes in class, but because my Blackboard has not allowed me to put in my quizzes, it's very difficult. But we will move forward. So this is homework, but I'm not looking for a grade right now. I'm not looking for you to submit it. Just do it. Do it as homework so you can understand how to solve the problems.